Hi everybody, in this video, which will be the last of our Light and Matter video unit series, we're going to discuss space telescopes and some telescopes of the future. So we'll start off with the leading question of why do we often refer to the best images as coming from the 2.4 meter Hubble Space Telescope, as opposed to ones like the twin 10 meter Keck telescopes or the 8.4 meter LBT or the 11 meter SALT telescope, when these are much bigger telescopes and you would think should have much bigger images. And the answer is because that resolution formula that we gave is diffraction limited. So even though those other telescopes have much better resolution in principle, that's only if everything is perfect. But as we know, our atmosphere provides turbulence, and this can create seeing limited conditions. Though nowadays, with adaptive optics and better adaptive optics techniques, we're starting to get around this. And the truth is that nowadays, the best ground-based telescopes actually are providing better images than the Hubble Space Telescope. But there's another issue as well. The Hubble Space Telescope has infrared and ultraviolet capabilities, and most ground-based telescopes, even the biggest ones, don't have these same types of capabilities that the Hubble Space Telescope has. So the Hubble Space Telescope was originally planned in the 1970s, but it was delayed by the Shuttle Challenger launch disaster in 1986. Finally, it was launched in 1990, but there was a problem. Unfortunately, the primary mirror had been, it was actually the most precisely ground mirror in history, but it was ground to the wrong shape. So that created some spherical aberration and the images were blurred. But they literally gave the Space Telescope glasses a corrective optics package, and these were installed in late 1993, so by 1994 it was in better working condition. In fact, this was something that really kind of, I guess, erased a lot of the early bad memories of the problems that existed. Unfortunately, they did have to block out the view of the faint object camera, which would have potentially been able to get some very precise images of some of the outer solar system bodies. So, in any case, follow-up missions have continued to keep the Space Telescope up and running, and cameras have been updated and allowed for observations in near ultraviolet and near infrared. And gyroscopes were replaced, but unfortunately with the grounding of the space shuttle missions, these gyroscopes will eventually fail. And after that happens, the Hubble Space Telescope will be decommissioned. So hopefully in the 2030s, like around the mid-2030s or so, NASA will launch the High Definition Space Telescope, which would potentially be an 8 to 15 meter mirror. The Hubble Space Telescope's mirror is 2.4 meters. And that actually would replace Hubble as NASA's flagship optical space telescope. It would be the true replacement for the Hubble Space Telescope. So here's a comparison of the before and after images of the same galaxy M100 with the before and after the repair that corrected the misground mirror. So nowadays, Hubble Space Telescope images, up until recently, had far better resolution than the best ground-based images, but as I mentioned, with the modern adaptive optics techniques, this has actually been overcome now. But Hubble has increased our knowledge of the solar system's understanding, particularly the formation of the solar system, characteristics about the objects in the solar system, as well as star formation, galaxy evolution, and cosmology, more than any other single instrument. And in some of these fields, one could even make the argument more than all other instruments combined. So, a picture of a nice star-forming region. Here's a picture of a large, massive star in the late stages of its evolution, and then a picture of the region of, say, a sun-like star during the late stages of its evolution as it's tossing off its outer layers. And here's another one of those. And here you can take a comparison of the resolution of an 8-meter ground-based telescope, the Subaru telescope, before much in the way of modern adaptive optics techniques were used, compared with the Hubble Space Telescope's image of the same galaxy on the right. Now, this does not mean that the ground-based telescopes had no place even before really good adaptive optics techniques were used. They did have their place. In particular, if Hubble found something very deep in the universe, then the ground-based telescope could be used to have its superior light-gathering capabilities to essentially dig deeper in the image itself. But for a while, the resolution wasn't quite as good. But nowadays, it is. And here's a picture of the Hubble Ultra Deep Field, showing some of the deepest views that astronomers have ever made of reasonably large sections of the sky. Now, in terms of the resolving power, as you know, the resolving power gets better as you look toward shorter wavelengths. So, if the Hubble Space Telescope is looking in the ultraviolet parts of the spectrum, it has a resolving power of 0.026 arc seconds. So that's pretty good. So here's a picture of it. Now, the James Webb Space Telescope is often stated as the successor to the Hubble Space Telescope. This is not quite true, because as we discussed, the Hubble Space Telescope has capabilities not just throughout the visible part of the spectrum, but also in the near ultraviolet and the near infrared. The James Webb Space Telescope, which is a bigger telescope, will mainly observe in the near infrared, as well as up to the mid-infrared. And of course, as you know, the infrared parts of the spectrum require a larger instrument to be able to have the same resolution. So, looking at the near infrared, James Webb Space Telescope will actually have not as good resolution as the Hubble Space Telescope has in the near ultraviolet. So that's something else to note. In addition, this so-called successor will not have the capability of looking throughout the visible part of the spectrum. It will not be able to observe particularly energetic objects unless their wavelengths have been redshifted to the near infrared by the expansion of the universe. It's a topic that we will discuss in a lot more detail in a future unit. The other thing about JWST is originally it was planned for launch in the mid to late 2000s with a price tag of about $500 million. But due to various poor management and other delays, that has now extended to over $10 billion, and the launch will be on October 31st of 2021 at the earliest, as of the making of this video in mid-December of 2020. But in any case, when it is launched, it will have a great capability of observing extremely deep into the universe, because due to the expansion of the universe, light that was originally emitted in the ultraviolet or visible parts of the spectrum has been redshifted to the infrared parts of the spectrum. Also, it will be able to look very deeply at newly forming star-forming regions, which are often hidden by dust from the people looking in the visible part of the spectrum. Now, speaking of which, infrared telescopes have been out there for quite a while now. In fact, one of the early ones was IRAS, and IRAS was put into space in 1983. And again, you need this ability to get infrared telescopes above most of the water vapor infrared absorbing effects of our atmosphere. So either on tall mountaintops or in space is where you need to be. Now, IRAS actually made a lot of news back in the 1980s when it observed the stellar system Beta Pictoris and found that when a mask was used to hide the bright light of the star, a dusty disk was found around this. This was one of the first hints that we had that scientists' ideas of planetary formation were actually correct. Nowadays, we have instruments like the Spitzer Space Telescope, which is, again, a space telescope. It's not as big as the Hubble Space Telescope for its primary mirror. The Hubble Space Telescope's primary mirror is 2.4 meters, and I think Spitzer's primary mirror is something like 0.85 meters. But nonetheless, the fact that it's a dedicated space telescope for the mid-infrared part of the spectrum has allowed us to get a very good improvement of our understanding of things like star-forming regions, early galaxies, etc. Now, the Herschel Space Observatory, which was launched in mid-2008, imaged in the far infrared, and this actually is a bigger telescope than the Hubble Space Telescope, but it needs to be because it's observing in the far infrared. And then in 2010, NASA launched the Wide Field Infrared Survey Explorer, the WISE Explorer, and it gave a very thorough mapping of the sky in the infrared and basically told us that there can't be anything larger than the size of Jupiter in the Kuiper Belt or Oort cloud. So if there is a missing planet out there, it's probably smaller than Jupiter. So given the Christmas season at the time that I'm making this video, here's a picture of the Christmas tree cluster taken by the Spitzer Space Telescope. And here's a nice picture taken by the Herschel Space Observatory. And here is an image of the Andromeda Galaxy taken first in optical, then infrared and X-rays, infrared being the Spitzer data, X-rays being, I believe, data from the Chandra X-ray Observatory, though it might be XMM Newton. I would have to check on this image. And then a composite image. What you notice is that when you look at different parts of the electromagnetic spectrum, you obtain very different complementary information about objects that are out there. In infrared, you can see the structure of the spiral arms of the Andromeda Galaxy much better than in visible wavelengths. What about X-ray and gamma ray telescopes? So here's the thing. X-rays are so powerful that they're not going to be able to bounce off of mirrors. You can't use mirrors for X-ray telescopes. What you instead need to do is use a series of nested mirrors where the X-rays strike at very low angles above the surface and are then directed into the detector. And this actually only works for X-rays. This does not work for gamma rays. So for gamma rays, you need to use something even more clever. So let me get rid of this gamma rays and say fix it, and it's fixed. Now let's take a look at how these work in terms of some of the images that they get. So first, the Chandra X-ray Observatory, named after Subrahmanyan Chandrasekhar, one of the most important astrophysicists of the 20th century. We'll have a lot more to say about him later in the course. It was launched in 1999. It was one of NASA's so-called Great Observatories, along with the Hubble Space Telescope. So it orbits Earth every 2.7 days, and among its contributions include better and different types of observations of supermassive black hole regions and galaxy centers, as well as pulsar observations and a new way of determining the Hubble constant. So here's a picture taken by the Chandra X-ray Observatory. And then one of NASA's other great observatories was the Compton Gamma Ray Observatory, launched in 1991. And this allowed us to study cosmological phenomena like gamma ray bursts, and also mapped the occurrence of aluminum-26, which is a radioactive aluminum isotope that only comes really from supernova explosions. It was common in our early solar system, but it has since decayed into other things. But we now realize that yes, this does definitely come from supernova explosions. This is a picture taken by the Compton Gamma Ray Observatory. Any idea what this is? This is the moon. So, because of the fact that gamma rays are so powerful that even the nested sequence of grazing incidence mirrors that work for X-ray telescopes, that this won't work for gamma ray observatories. Instead, you need to have the photons, the gamma ray photons, come into some sort of material, and based on the angle and intensity, you can make an estimate of the direction of the sky from which they came. But still, your estimate is not going to be very precise because of the nature of these particles. So in other words, yeah, the diffraction limited formula, and it does not work for X-ray telescopes, and especially not for gamma ray telescopes. Now, what about radio telescopes? Radio telescopes have a big advantage over optical telescopes, and that's that they can be used during the daytime. And also, because the wavelengths are long, they don't really require very precise mirror constructions. You can have rounded parts on the dish, imperfections on the dish, bruises, panels taken out, and it won't really affect the imaging that you're trying to do. So very large telescopes can be made at a much lower cost than what would be used to make similarly sized optical telescopes, and they can give you pretty precise images. This is an image of the galaxy Cygnus A, which is about 800 million light years away. The galaxy is this little tiny thing here, but it has these giant millions of light year long radio lobes that actually make it the second, or make it the third brightest radio source in the sky after the sun and a supernova remnant in our galaxy. So it's really interesting. Now, we'll come back to radio telescopes soon, but you do need to know about the great observatories. There are 4 of these. They're the Hubble Space Telescope, the Compton Gamma Ray Observatory, the Chandra X-ray Observatory, and the Spitzer Space Telescope. Hubble for visible, Compton for gamma, Chandra for X-ray, and Spitzer for infrared. Nowadays, a number of these have been either decommissioned or superseded. For example, Compton's been superseded by Fermi, Chandra is superseded by XMM Newton and others, and Spitzer is no longer in operation because its coolant ended up running out. As the years go on, in fact, I would say in 2020, I'm not even really going to have my students know these so much because they're a little bit outdated, so to speak, but they're nice to know about for historical purposes. So you can turn to the person next to you and state which of the primary wavelength bands is studied by each of the 4 great observatories. So you can pause the video at this point. So now that you've thought about that, just recall the 4 great observatories are the Hubble Space Telescope, which mainly observes invisible, the Compton Gamma Ray Observatory for, well, surprise, surprise, gamma rays, the Chandra X-ray Observatory for, surprise, surprise, X-rays, and the Spitzer Space Telescope for the infrared part of the spectrum. And I have a link here to a nice YouTube video showing how data are put together to create visible images from non-visible light from 3 of NASA's great observatories. Of course, you don't need to do this with non-visible light from the Hubble Space Telescope so much. And I'll try to remember to post the link to that video in the video information on YouTube. And the results are interesting images of the galaxy M101, showing more features than what our eyes are able to see. In fact, here is the link to that video, in case I forget to put it in the notes. I don't want to show it as part of the video that I'm making here because I'm worried that YouTube will block it, as they have done before when I've tried to show clips sometimes of videos that other people have made and posted. But there's the link, and I'll try also to post it in the notes. Now back to radio telescopes. As I mentioned, we have more to say about those. Radio telescopes are the largest observing telescopes in the world, by far. I mean, think about it this way. The biggest optical telescope in the world, the SALT telescope, South African Large Telescope, has a primary mirror with a width of 11 meters. That's like 35 feet, 36 feet, whatever. And meanwhile, just a basic radio telescope might have a dish that has a width of like 50 feet or 60 feet or 100 feet. And the biggest ones are much bigger than that. So there is a downside to that. Because of the fact that radio waves have longer wavelengths, that means that you need a much bigger instrument to have a similar type of angular resolution to a visible telescope, like say the Hubble Space Telescope. So remember, the Hubble Space Telescope has an angular resolution of 0.025 arc seconds when it's observing in the UV, whereas a 140 foot, that is about 40 something meters radio telescope would have an angular resolution at a wavelength of 21 centimeters, which is a common wavelength for observing hydrogen, a resolution of 21 arc minutes. Again, compare that with 0.025 arc seconds. The Green Bank telescope, which is the largest mobile telescope in the world with a diameter of 100 meters, has an angular resolution of 9 arc minutes. So there's the 140-foot one, also a Green Bank, and there's the bigger one with the diameter of 100 meters. But yeah, 9 arc minutes is the angular resolution in this instrument. Now, there are tricks that can be used. The Very Large Array in New Mexico has a system of 27 radio telescopes that are all linked up together. Now, a dish does not have a diameter of 20 kilometers. That would be completely unreasonable. You're not going to have a single dish with a diameter of 12.4 miles. But instead, what you can do is you can spread these individual dishes out over a triangle that has a size of about 20 kilometers. And by linking up the wavefronts in computers and having the computers sort out the wavefronts that are currently at each particular time visible on each telescope, they can attain an angular resolution of 0.1 arc seconds. Now we're starting to rival Hubble here. And by using the same technique and linking together radio telescopes all around the world, you can create the Very Long Baseline Array with an angular resolution of 0.0005 arc seconds. So at the end of the day, using modern computing capabilities, we can create radio telescopes that have angular resolutions that are much better than any other telescope in the world. So here's the VLA in New Mexico, and here's a map showing a number of the telescopes in the VLBA. There's also one at the South Pole as well, and I think one in the UK. These telescopes in the VLBA were teamed up recently to create what we call the Event Horizon Telescope, to try to make images of the black holes at the center of the Milky Way galaxy and the black hole at the center of the galaxy M87. These black holes were chosen because these, combined with their distances and their sizes, actually have the largest angle in the sky. It's interesting that the largest angle for a black hole in the sky is actually created by at least among the two, is created by the black hole at the center of a galaxy that's 50 million light years away. And here is the image of that, the image created by the Event Horizon Telescope of the black hole at the center of the galaxy M87, at the center of the Virgo supercluster, like 55 million light years away. Now, the central part of this donut, it's not actually the black hole itself, it's more like the shadow of the black hole. But the way the light is bent around by the gravity of the black hole confirms not only the predictions of general relativity of how light ends up behaving in the environments of these things, but also confirms that these things actually exist. In other words, if this was like some sort of solid surface that was held up by the laws of quantum mechanics, then this would look a bit different. But instead, you have a relatively sharp cutoff in the light ring around it into the central shadow. Now, NRAO used to have another big radio telescope as well that was also steerable, but unfortunately it collapsed, and apparently it was zapped by aliens. So this is many people are saying this. This is being covered in a news source. Many people are saying this, and so this was apparently zapped by hostile space aliens. So I'll leave this to you to determine the veracity of this particular source. Now, there are bigger telescopes than that. The Arecibo telescope at Puerto Rico, when it was built, was the largest single telescope of any type in the world. It was about 1,000 feet wide, and that meant that it was immobile. In other words, the only way that you could observe different parts of the sky was either wait for Earth to rotate or steer the antennae above the dish so that the rebound of the radio waves would end up going into different spots depending on where you wanted to observe in the sky. Unfortunately, late 2020, after all, it is 2020, this telescope collapsed. It was built into a natural sinkhole, and the antennae ended up collapsing. They tried to support them. They collapsed further, and now there are currently, as far as I know, no plans to rebuild this facility. Fortunately, by this point, Arecibo had been superseded, but in the meantime, it had been fundamental or instrumental in allowing us understanding into other parts of astronomy that had previously not been possible, because the combination of its resolution by being 1,000 feet wide and its huge light gathering power by being a single 1,000-foot wide observatory allowed us to do things that you couldn't do with other observatories. For example, the first evidence of ice on the planet Mercury, of all places, was found using Arecibo. In addition, it was occasionally used for searching for evidence of extraterrestrial civilizations, as well as sending signals out to potential extraterrestrial civilizations. So here's a picture of it when it was up and running, and as you can see, it was built into a natural sinkhole in the mountains of Puerto Rico. It has now been superseded by the 500-meter aperture spherical radio telescope, FAST, which was recently completed in the mid-2010s in Guizhou province in China. It's nicknamed Tianyan, meaning heavenly eye. Tian meaning heaven, Yan meaning eye in Chinese. It is now the largest single telescope of any type in the world, and it's therefore a significant upgrade to Arecibo. And fortunately, it started its operations just in time, because, as we just saw, Arecibo is no longer. Here's a picture of Tianyan. That is the FAST observatory. So, very nice. Similar idea, built into a natural sinkhole, and so hopefully they don't end up having the same types of issues that Arecibo recently had. There's also the Deep Space Network. Essential question that we had at the beginning: how do astronomers communicate with all of these interplanetary spacecraft that we have throughout the solar system, orbiting planets, on planets, orbiting around moons, asteroids, etc.? So how do we do this? This is the Deep Space Network. We use a network of various radio telescopes around the world. I believe that Green Bank is sometimes used in this end, but it sends and receives these types of communications. In fact, in a similar manner, you may have a radio telescope. If you get your cable service from Dish Network or DirecTV, you have a radio telescope mounted either on your roof or somewhere outside of your home. And this receives these types of signals from the satellites. Well, if you're trying to receive a signal from something that is much farther outside than just Earth's orbit, you need a much bigger dish, which is where the Deep Space Network comes in. What about observing in microwaves? The microwave region being kind of part of the radio, part of the infrared, depending on how you think of it, but it's kind of in between. It's a band in between. And the reason that microwave observatories are particularly important, at least the main reason, is because the Big Bang, which originally created a whole lot of infrared radiation and visible radiation when that light was let through about 370,000 years after the actual event, for reasons that we will discuss in the cosmology unit. Well, that has now been redshifted to the microwave parts of the spectrum. And detailed mapping of this over the past decade has narrowed the known age of the universe down to, at least if you believe these particular measurements, of about 13.8 billion years, with a relatively small uncertainty. Now, as we'll discuss in the cosmology unit, there's a bigger uncertainty than this, because using different techniques, other astronomers believe that the age is more like about 13.6 billion years. But nonetheless, we can use microwave mapping to uncover a whole lot about the early universe. So The existence of this radiation was predicted back in the 1940s, then it was discovered in the 1960s, and then mapped over the entire sky, first in 1992, giving us this image. But then, improvements in the technology have allowed us to get more precise maps, first with the Boomerang Observatory right here, then WMAP right here, and finally the Planck Observatory giving us the most precise map of the region, basically at the edge of the visible universe, the echo of the Big Bang to date in this image right here. Some telescopes of the future. What is out there on the table? Well, the ALMA Observatory is a system of radio telescopes that is still in the process of being completed. It's been performing some great observations already. In fact, I think the last of its dishes is just in the process of being commissioned, so to speak, and linked up to the whole network. And then we also have a few visible observatories as well. And as you can see, we have this unfortunate system of uncreative names. For example, GMT is the Giant Magellan Telescope. The EELT, or just ELT, is the Extremely Large Telescope, and these are in the process of being built. So, ALMA, the Atacama Large Millimeter Array, is a group of 66 radio telescopes in the Atacama Desert of Chile. It began operations in March of 2013, and in order to really link these things together, one of the world's biggest and most powerful supercomputers, at least at that time, was being used. So here is a picture of early ALMA telescopes, and here's an early ALMA image, so the antenna galaxies combined with a Hubble Space Telescope image. So these radio emissions tell us a lot about some of the neutral hydrogen gas and other types of molecular compounds that are out there in galaxies. So it helps us to map things like neutral hydrogen, carbon monoxide, etc., that are often present in galaxies. Now, in the visible part of the spectrum, the 30-meter telescope will hopefully start being built, but construction of this has been delayed until at least 2021. In fact, the completion time on this needs to be updated to about 2024. So I will say fix it, and it's been fixed. But there were a significant number of delays with this because there were protests by Native Hawaiians and legal bureaucracy about building a telescope at the top of a mountain that they consider holy, Mauna Kea, which already has a number of large observatories already. But yeah, the 30-meter telescope, once it's completed, will have a primary mirror with a diameter of about 30 meters. That is about 100 feet. Here's a artist's rendition of this. There's also the Giant Magellan Telescope, which will contain 7 8.4-meter mirrors in a honeycomb-like shape to create one mirror. So here's an artist's rendition of this, and this will be completed around 2025. And then finally there's the European Extremely Large Telescope that will have a primary mirror with a diameter of 39.4 meters and will have both visible and near-infrared capabilities, and this will be completed, or it's scheduled for completion around 2024 as well. So here's an artist's rendition of this observatory. Notice its size comparison with a large pickup truck down here. And EELT and GMT and TMT, these observatories will give a good ground-based complementary capability to not only the Hubble Space Telescope, but also the James Webb Space Telescope. In fact, in some ways, the delay of the James Webb Space Telescope has kind of allowed the James Webb Space Telescope to be perhaps superseded in a lot of its capabilities. It will still be above the atmosphere, so that will be significant. But the fact that we have these very large ground-based observatories that have infrared capabilities and also visible capabilities, as well as what will probably end up being the world's best adaptive optics capabilities, leads us to believe that astronomy in both the visible and the infrared part of the spectrum has a very bright future. So that is the end of our videos for the third unit of our course, Light and Matter and Telescopes. The next part of our course will start getting into the meat of astronomy with studying the solar system. That will be Unit 4, and I hope to see you then. Thank you.